welcome to tonight's lecture. That is on concurrent engineering and rapid prototyping. This is going to be the final lecture of the CAD/CAM course. And, we're going to look at two technologies. One is a technology, one is more like a strategy or an approach in manufacturing. Now, by way of introduction, we first want to talk about concurrent engineering. It's actually another powerful CAD concept that has had some changes since the 90s. But in this concept, what basically happens is that there's an instantaneous communication between the designer, analyst, and then manufacturing. Now, if there are any changes that are supposed to be made, they are immediately passed on to the others, and the product is modified without delay in the manufacturing process. So often you have the customer management and the marketing people also coming to join as part of the process. So concurrent engineering, in a nutshell, gives you a situation where there is instantaneous communication between the designer and analyst. As a result of that, it has been observed to save valuable time, and then it helps the product out to the market very quicker. They are also able to ensure that, of course, products that could take years from concept to actual manufacturing now takes a couple of weeks, and sometimes maybe a few weeks or a couple of months. Now, also because there is that communication between these bodies that are involved in the manufacturing process, the product becomes better and cost effective. Now, when it comes to rapid prototyping actually refers to a class of technologies that can automatically construct the physical models from the CAD data. Now, what happens in the process is that the part is created by a CAD package and downloaded into the rapid prototyping machine. Then the machine immediately manufactures the part using a plastic material. Now, this is a good example of concurrent engineering. Sometimes we refer to this as art-to-part concept. That is, you have the model and then you have the part in your hand within a short time. Now, in this study, we should study about these two engineering processes and the role each play in part of product development. So we move on to our learning objectives. After we study this course, we should be able to explain some terminologies used in concurrent engineering. We go through a list of terminologies. We also have to be able to explain and list the global objectives of concurrent engineering. We should be able to list the specific objectives as well, and the conditions required for successful implementation of concurrent engineering. We should also be able to explain the various forms or various rapid prototyping techniques commercially available. The unit is structured this way. We look at the first section, which talks about the concurrent engineering. The second section, we look at the rapid prototyping, and then we look at the rapid prototyping in general as a technology, and then we will look at the rapid prototyping technique. That's the 6 techniques that are commercially available. Now, when it comes to concurrent engineering, if you want to define the concurrent engineering, basically has an objective to simply detail the design while simultaneously developing production capability, full support capability, and also quality. So it's like having a simultaneous approach to the engineering process. Now, it is a sort of methodology that uses a multidisciplinary team to carry out this concurrency. Now, there are tools for concurrent engineering or some form of algorithms or techniques in the software, and the expertise and judgment of people who in a nutshell make this a complete production sequence. Now, the terminologies used in concurrent engineering are follows. Now, you have assemblability, which is an evaluation of how easily and cheaply a product can be assembled. We have axiomatic design, which looks like the use of some accepted truths and corollaries in concurrent engineering. We have, of course, the concurrent engineering itself as a technology. It is looking at the entire life cycle of the product simultaneously using the design team and automated engineering and production tools, as well as the other teams, the marketing and all the other teams involved in manufacturing. Now, if you move on into the terminologies, I'm just going to elaborate on a few ones. We have what we call controllable factors. In concurrent engineering, we're talking about the elements that can be controlled during the production process. Exactly, examples are dimensions, tolerances, and material types. Now, if you the other terminology we also talk about is design science. Now, when we use design science, it's actually used to design products by, let's say, using catalogs relating function to feature. If you have process where you want to design a product by using some catalogs that have already been developed, and you are relating the function of the product to feature, then we're saying that you're following a design science. Meaning, you look at this design as a teachable science and not an art. So in engineering, that is how engineering views design, concurrent engineering, to say that design is a teachable science, not an art. Now, design for assembly, DFA, simply a technique by which the products design for ease and economy of assembly. So we want it to be easily assembled and also at a cheaper cost. Now, design for manufacture is also in the same league as design for assembly, where you are designing for ease and economy of manufacture. We have some guidelines which actually guides design for manufacture techniques, and they are simply some rules of thumb that we use in the design for manufacture process. And we can talk about domain experts. Domain expert is someone who basically is an expert in that domain in a particular area. For example, in an area of maybe process planning. Then we have MEA, which is failure mode evaluation analysis. Sometimes you can approach design from looking at identifying and preventing the various modes of product failure. Sometimes you rank the modes of failure from least impact and the path function, and address them one by one during the redesign process. So you can use that as a means of redesigning the product, which is failure mode evaluation analysis, which is we are identifying and preventing the various modes of failure, and you can use that technique to map out and redesign a product. Now we have liaison sequence, which is establishing. We have liaison sequence, which is an establishment of a relationship among components of assembly in order to enumerate all possible use of assembly technique. Now we have manufacturability. And then we have product development team, producibility, product life cycles, strategic approach to product design. These are a few other terminologies which you can read for the meaning. You come to serviceability. Then we talk about signal to noise ratio. This is also a very important terminology which talks about a measure of a system's response resistance to being influenced by noise. Now, noise here, we could talk about it as performance. So a signal is a measure of performance, and noise is a measure of uncontrollable factors. So if we talk about signal, then we are talking about the performance of the machine or the product, and then noise talks about uncontrollable factors. So if you want to do a signal to noise ratio, then basically you are looking at the performance of the machine as a measure of the noise, that is the uncontrollable factors that are in the machine, that is the deficiencies that you could not control, or you can't do so, you couldn't do much about. Now, we talk about unified life cycle. Unified life cycle engineering is also a new engineering approach. That's a concurrent engineering architecture developed by the United States Air Force. Now, what they emphasize in this particular engineering approach is the integration of models which include design rules, design knowledge about the designer's intent. So you have design rules and design knowledge that guides the designer's intent. So the designer may have some idea, and then his intentions will be guided or will be integrated using design rules and some knowledge about the designer's intent. So he may have some idea to design something, so we get to know the knowledge about his intent, and then we apply some rules, some design rules, to really get that. That is unified life cycle engineering. The unified life cycle engineering is quite a broad engineering technique or architecture. Now, uncontrollable factors, these are elements which are not controllable, like noise factors. Example, for instance, weather and maybe the stock market performance of the whole company in a broader picture. Then we have value engineering, also as a technique for measuring the quality of the design as a ratio of the performance of the life cycle cost. So we have the value engineering now is a new area of engineering which is being practiced. So basically looking at the quality of a product design as a performance or a total life cycle cost. So you'll be bringing in environmental effects, and so if we say the product has a value, then all these have been actually looked at, whether the product is having an impact on the environment or not. These are all other issues that we can look at as terminologies in concurrent engineering. Now, when it comes to concurrent engineering process, as we have already defined, it's basically the integration of product design and process planning into one common activity. It helps to improve the quality of the early design decisions that obviously has a very tremendous impact on the life cycle cost of the product, because when you are designing and you make some decisions, it takes the design into a particular direction, and based on that, the direction the design goes, it may have a serious impact on the final cost of the product. So if you take concurrent engineering, you can look at it in this manner, which we're going to look at in this figure here. You have basically the design coordinator, and then the design coordinator sits in the middle like a wheel, and then you have various domain experts, which they are in inspection, marketing, sales, packaging, function, serviceability, manufacturing. All these areas will have domain experts. That is manufacturing, servicing, assembly, function, inspection, marketing, sales, and packaging. They will be on the various points on the wheel. So you notice that the wheel has a double arrow coming across. Now, if we want to expand this, the arrows actually move across each other. That is, inspection will be talking to marketing, marketing will be communicating back. Same time, marketing will be talking to sales, sales will be communicating back, marketing will be talking to the design coordinator, and then there will be that back and forth interaction. At the same time, marketing will, inspection will be talking to the design coordinator, there will be some interaction back. So there is a whole wheel that all the domain experts are on this wheel, and they will be working together to achieve an efficient product for the design. Now, you have all this group actually in the process, in the concurrent engineering process. So what is happening is that you have communication among the experts, as you can see from the arrows. So there are a number of experts. Typically, we look at them from here: manufacturing, marketing, some inspection and assembly experts. Now, the experts have the mission to conceptualize the product and optimize it until a consensus agreement is reached on the functionality, producibility, and cost constraints. So these are their roles, more like their objectives. So they will be working through the concepts, be debating about it, going back and forth, looking at the various conflicting dynamics until they agree or reach a consensus on the functionality, producibility, and cost constraint. So the design then moves from the designer out to the experts, who discuss it and suggest design changes to satisfy these three constraints. Then the design is then passed to the designer, who resolve these conflicts and suggest changes, modify the designer, send it out again for evaluation. So this process continues in a cyclic manner, and it's like it's going around the wheel, because all the domain experts will have to be in the know of what is happening. So if you look at concurrent engineering, concurrent engineering has some global objectives. Now, you can think about it as accomplishing about 5 interrelated elements. These elements are really interrelated in some way. So the 5 are follows. The first is there will be a careful analysis and understanding of the fabrication assembly process. Now, Once this global objective is able to be achieved, it allows the engineers or the designers to predict the performance of the product and select a production scheme from among the alternative processes. So, to be able to practice concurrent engineering or achieve concurrent engineering practice, then you have to carefully analyze and understand the fabrication assembly process so that you can make changes or you can make suggestions about what alternatives that are available. Now, the second key thing you need to know is that it aids in having a strategic approach to the design. Now, of course, this will be conceived to support a specific strategy for making and selling the product. Now, of course, the product will have to be made to marketing specification for market life, shelf life, and usability. That is key. But there will be a particular strategy which will be developed by the team and say that, okay, we're going to this level, we introduce the model this way, and then we will look at a gradual development of this model from this stage to another stage. We release a new model at this stage, and they actually do this to ensure that the product has a sustained life. Like they actually increase the life cycle of the product by having a strategy by which they use in design. So strategic approach to the design is also key. Now, of course, the third objective will be a rationalized manufacturing system design, which is coordinated with product design. And again, the economic analysis, that's for the rationalized manufacturing system. Of course, you will have to look at the manufacturing capabilities. Now, when you conceptualize a product, the manufacturing system must be considered such that the concepts that will be developed have in mind the manufacturing capabilities and constraints, so that you don't just sit down and develop anything thinking that it can be manufactured. So there should be some rationalization of the manufacturing system design, which will then coordinate with the product design. So that is the third point. The fourth point talks about economic analysis of the design and manufacturing alternative to permit rational choices among the design alternative. That is, you have to actually do an economic analysis to find out how feasible a particular design is, and of course the cost-benefit analysis, so that you will then make a rational choice among the various alternative designs that you have to consider. Now, there is also a need to have a product and systems design that is characterized by robustness. Now, here it means that you want to design in such a way that the design is resistant to unpredicted noise or errors in the production and function. Now, the product's function is as resistant as possible to variations in dimensions within a particular tolerance. You'll notice that this product and system designs, which are characterized by robustness, is practiced among some known automobile industries. You check a particular model of a car and you notice that the design is consistently in a particular way. A typical automobile industry you can use is the Benz automobile industry. You notice that their designs are very robust. They do few changes here and there because it's a strategy. So they have a product and system design that is so robust that it is, resistant to some changes in dimensions and tolerances and function. Benz cars have maintained some dimensions and some, design, the shape and other parts have consistently remained as they are because of this concurrent engineering strategy that they employ in their manufacturing. Okay. Now, when it comes to the specific objective, we talk about the global objectives. The global objective, quickly, there should be, of course, there will be need to carefully analyze and understand the fabrication assembly process. There's going to be a strategic product design, and that is the product should be made to marketing specifications for market value, shelf life, and usability. And of course, this rationalized manufacturing system, which is designed and coordinated with the product design, and economic analysis of the design and manufacturing alternatives, which will permit rational choices. The product and system design have to be characterized by robustness. Okay. Now, specific objectives within the elements of concurrent engineering as follows. Now, based on these global objectives, specifically, this is how the companies will respond to these global objectives. That is, they avoid components or features that are unnecessarily expensive to produce. For example, specifications of surfaces that are smoother than necessary, wide variations of wall thickness and all that, too small fillet radius, radii, and some internal apertures of some components that may not be necessary. So you avoid component features that are unnecessarily expensive. There are some designs or features that have no effect on functionality, and therefore you have to keep it simple and keep it cost effective. Now, specifically, that is one aspect they will have to consider. And then the second is to cost or make the optimum choice of materials and processes. Because if they do a careful analysis of the manufacturing process, they will cost and make optimum choices. So that is, for example, if a component can be cold work and finish, machined rather than machined from a bar sock or whatever, then they will look at the cost involved. Now, to align all decisions designed to support the goal to satisfy customer expectations. Now, that is also a key point because specifically, all the processes that are being are taking place is designed to satisfy the customer's expectation. And what are the customer's expectations? Quality, cost, productivity, speed, that is time to market, and user requirements. Now, the fourth point is retain customer and profitability. Very key to concurrent engineering because ability to retain your customer is so key. Now, it is quite serious if there's a manufacturing error. There are a few examples down here which you can just look at. At some point in just this early 2000s, Sony had a problem with their Sony VIO laptops. They had to recall a lot of batteries, about 90,000 batteries. That is 90,000 computer batteries. And that resulted in lawsuits here and there, compensations paid. In fact, that recall cost them $429 million combined, and it resulted in a 94% profit shrink. And eventually, Sony had to leave that laptop business more or less. So now you don't even see the Sony VIO laptops any longer. This is having a problem with the battery. So that is the cost of a wrong design, and that can really hit the company. Ford had issues with the design. Now, if you remember, just a few years ago when American had the bailout, where most of their auto manufacturers were running out of business. They were not making profits, and they were in danger of being closed down. And the U.S. government has to bail them. Now, Ford recorded about 5.8 billion loss in profit, a third net loss. Okay, and that led to 16 manufacturing plants being closed down in the United States, leading to 45,000 jobs lost. There are cities in the United States like Michigan and the likes that are automobile cities. You can count at least an individual from a household who works in one automobile company. That is how the city is. So if the companies are underperforming or posing losses, that can have a very severe impact on the economy nationally and also locally in that area. So it is very important to retain your customer and also your profitability in concurrent engineering. Right. So if you look at manufacturing in the product life cycle, if you take a typical manufacturing product life cycle, we do some market analysis by the R&D group. Then based on their findings, there will be engineering modeling, and then you have the product design group, design and of course technology. Then the process design goes through. Then once the process design is also through, we have prototyping taking place, and then we have production system being planned for manufacturing to begin, and quality control then comes in, and finally you have the field warranty and then service. So you notice that the CAD CAM is extensively being used in the product life cycle. At some point you have rapid prototyping taking place, you have cellular manufacturing, and then you have some process control in terms of the quality control taking place. Now, when you look at typical product life cycle, let's look at conventional product design here. Now, from that life cycle, basically, if you look at a conventional product design, what used to be before concurrent approach actually came in. If a designer has an idea or someone has an idea, it is passed to the product design. The product design the product, passed to manufacturing. Manufacturing manufacture the products, pass it to assembly. That's it. Send it out there for maintenance. That is on the field. Now, you will see this approach was basically called over the fence approach, because nobody knows what was going on in any section. The ideas come, roll out to thrown over the fence to the product design team. They also sit and work on their own, and once they come out with the design, push it over the fence to assembly and maintenance and the likes. But the birth of concurrent product design approach, notice that this product design team, the marketing or whatever the ideas may be coming from manufacturing, assembly, maintenance team, they'll be working concurrently. They'll be talking to each other, and there's better collaboration between the different phases. So what you notice there is that there's a function overlap, which leads to a shorter total time to market. And that is shown by this strip here. So now companies are want to move away from the serial, this is what we call the serial product development process, because concurrent engineering addresses all issues related to the product life cycle. at the product design stage from the concept to the disposal. If you practice this approach, the danger you have is that, yes, the product designer will sit there and design. He may send it to manufacturing. Manufacturing will spot some errors and throw it back to design. And then design will do something, throw it back, and the time can even stretch further. But once the designer is designing the product, manufacturing, assembly, maintenance, all the teams are in the know of what is going on. So they can offer useful advice that can be factored into the design. And that makes the process far more quicker than it will otherwise be. So that is what the impact of concurrent engineering on a conventional process of product design. So you could see over the year that there has been an evolution to concurrent engineering. First, there was the idea of the sequential engineering, which we just talked about, over the fence approach. Then it came into a centralized approach where now you have the design coordinator sitting here, and then each of the domain teams will be sending their information or feedback. The design coordinator will be talking back to them and be giving the suggestions and taking the inputs. Then we notice that they may be coming out with conflicting variables or inputs. So the centralized design, that is, we move from sequential design to centralized design and move on to the concurrent design process, where now everybody is talking to everyone, and that approach is what is being used to realize design of late. So that is the evolution from concurrent engineering to from sequential to concurrent engineering. So when it comes to concurrent engineering, if you really want to successfully implement concurrent engineering in your company or your factory, then there has to be these four things which has to exist within the organization. First, the concurrent engineering has to be supported by top management. The product team or the members have to be dedicated for the application of this strategy. And each phase of the product development has to be carefully planned before actual application. Now, the new product lifecycle also has to fit into the existing product program life cycles of the company, because if not, companies will be very reluctant to invest in new tools or equipment for manufacturing. Now, benefits involved in concurrent engineering is that it reduces time for design concept to market launch by 25% or more. It reduces capital investment by 20% or even more. So this actually gives you an opportunity to either reinvest more, or you can actually make some profits. Reducing time to market line by a quarter is very important, because that strategically puts the product in the market, and you are most likely to reap a lot of benefit in terms of profits. Now, successful implementation of this concurrent engineering will come from the fact that it supports total quality from start of production, with earlier opportunities for continuous improvement. Now, it simplifies after sales service and also increases product life cycle profitability throughout the supply system. So that is concurrent engineering. Now we're going to move on to our next lecture, which is our next topic, which is rapid prototyping. Now, when it comes to rapid prototyping, we say that it's a term that is used to refer to a class of technologies that automatically constructs physical models from a computer design data or CAD data. Now, what the technique involves the use of what we call three-dimensional printers, which allow the designer to quickly create some tangible prototypes of the designs rather than just having a two-dimensional picture, such as a drawing on a paper. Now, such models have numerous uses. One, they make excellent visual aids for communicating ideas with co-workers or customers. In addition to that, the prototypes can be used for design testing. In addition to the prototypes, you have techniques that can be used to make tooling, which referred to as rapid tooling, and even production of quality parts in rapid manufacturing. So now the process is not just for manufacturing prototypes, but it is in rapid manufacturing. So when you take small production runs and complicated objects, rapid prototyping is often the best process available, because when the product is more complicated, rapid prototyping actually is the best technique that can be deployed. Now, let's look at the process, basic process in rapid prototyping. Though there are several techniques that are involved in rapid prototyping, they all employ the same basic 5-step process. Now, the steps are: 1, you create a CAD model of the design. You convert the CAD model